Hello everybody, in this video we are going to study about chemical bonding. As we know that when two or more atoms come together, they form a molecule. Therefore, there must be some force that holds these atoms together. And the force of attraction that is holding these atoms together, we call them as chemical bonding. So there are different types of bonds that are found between atoms to form a molecule. So first type of bond is ionic bond. Ionic bond. So in case of ionic bond, complete transfer of electron takes place from one atom to another. In this case, complete transfer of electron takes place. For example, in NaCl, an electron from Na gets completely transferred to Cl to form NaCl. This gives us NaCl. They come close together because when an electron is transferred from Na to Cl, Na becomes positively charged and Cl becomes negatively charged. So these two charges attract each other and they come together. Now, since the questions in IIT JEE are mainly theoretical from this chapter, therefore we are going to study this chapter in a different fashion than whatever we have studied in earlier chapters. Therefore, in this chapter we will be encountering questions along with the theory. We are not going to discuss questions separately. We are going to discuss questions along with the theory so that you can know what concept can be applied and at what place. So in case of ionic bond, complete transfer of electron takes place, and in case of covalent bond, electrons are shared. For example, in Cl2. In chlorine, an electron is shared in between so that they both can fulfill their quota of 8 electrons and can attain noble gas configuration, and thus they both can be stable. So in this case, electrons are shared, but in this case, in NaCl, electrons cannot be shared because if it gets shared, sodium will not be more stable than it will be by leaving one electron. Therefore, sodium prefers to leave one electron than to share one electron. Hence, in this case, ionic bond is formed, but in this case, covalent bond is formed. Now, the major factor that affects the behavior of the type of bonds formed is the electronegativity of elements. It is nothing but, by definition, electronegativity is the net tendency to attract a shared pair of electrons towards itself. So suppose there is a molecule of HF. So in this type of bond, electrons do not lie in between. In fact, they lie somewhat towards fluorine side, somewhat here. This is because electronegativity of fluorine is very much greater than that of hydrogen, and therefore fluorine attracts this shared pair of electrons towards itself, and hence this fluorine gets partially negatively charged, and this hydrogen gets partially positively charged. So therefore, by observing the behavior of this bond, we can say that fluorine is more electronegative than hydrogen. Pauling pointed out that for any pair of atoms AB, the electronegativity difference given by Pauling, it gave that electronegativity difference between any pair of atoms AB is equals 0.208 under root of delta, where delta equals EAB minus half of EAB. AA plus EBB, where EAB and EAA and EBB are the experimentally determined bond energies of AB, A2 and B2 respectively. And delta is in kilocalorie per mole. Remember, delta is in kilocalorie per mole. Okay, but later on delta was subsequently modified as, delta was modified as delta equals EAB minus under root EAA dot EBB. Okay, and to prove this, to arrive at this conclusion, Pauling, he adopted XH, that is electronegativity of hydrogen, as 2.1 and he took it as reference. So in doing so, he did this, he took XH to be reference, XH equals 2.1, he took it as reference. This is nothing but an arbitrary value. So from here he got the value of electronegativity difference as 0.1017 under root delta, where delta is in kilojoule per mole. Okay. Now from this expression, from the difference in electronegativity expression, he devised an expression for percentage ionic character. Percentage ionic character is nothing but, suppose in this case, since HF has got partial negative character and hydrogen has got partially positive character, therefore they have got a little bit of ionic character in themselves. So by electronegativity difference, he arrived at a conclusion of percentage ionic character, and its formula is 16 into XA minus XB plus 3.5 into XA minus XB squared. Okay. So from this he said that covalent bond AB is said to have 50% ionic character if electronegativity difference is 1.7, or these different theories evolved expressing different values of electronegativity difference for different values of ionic characters. Now let's discuss about dipole moment. Dipole moment. Mathematically, dipole moment or nu equals E into D, that is charge, unit charge into distance between two atoms, or by using definition, it is just the polarity of molecule as a whole, or as a whole is the vector sum of the individual bond moments. Okay, so in this case the polarity of the molecule, the measure of the polarity of molecule is known as dipole moments. Mathematically it is E into D, where D is 10 raised to the power minus 8 centimeter or 1 angstrom, and value of E is 10 raised to the power minus 10 ESU. So therefore mu is of the order of 10 raised to the power minus 18 ESU. So because the value of distance of bond length is of the order of 10 raised to the power minus 8 centimeter, and the volume of charge is 10 raised to the power minus 10 ESU. So mu is of the order of 10 raised to the power minus 18 ESU dot centimeter. Now if we convert this into dBi, then 1 dBi equals 3.336 into 10 raised to the power minus 30 coulomb centimeter, or from here it is equal to 10 raised to the power minus 18 ESU centimeter. and 1 unit charge, that is E here, is taken to be as. Now in this formula you will be given the value of D and you will be required to calculate mu. So 1 unit charge, 1 unit charge E equals 4.8 into 10 raised to the power minus 10 ESU. Remember this. So from dipole moment, the value of percentage ionic character was devised, and this expression is the percentage ionic character equals observed dipole moment divided by theoretical dipole moment. Theoretical dipole moment. So this expression gives us the value of percentage ionic character. Now, one thing that you should keep in mind that lone pair have got their own dipole moment or their own polarity. Okay, so let's discuss an example. That suppose you are given with NH3 and NF3. Now compare dipole moments or dipole moment of both. Now how will you do that? You know that the structure of NF3, by the way, by looking at these two structures NH3 and NF3, before looking at these two structures, you will say that the dipole moment of NF3 must be greater than that of NH3. Okay, but just let's see what can be the reason. Structure of NH3 is somewhat like this. Okay, so nitrogen is pulling electrons from here, therefore the polarity of these three bonds is towards nitrogen, and there is one lone pair here, and one lone pair pulls electron towards itself as well. Therefore polarity of this lone pair is towards upwards. Therefore net dipole moment here is upwards. It is very much upwards. But in case of NF3, the situation is reverse. In this case, since fluorine has got more electronegativity than nitrogen, fluorine pulls the electrons towards itself. And here the lone pair pulls the electrons towards itself. Therefore, in case of NF3, dipole moment is very less, because here this lone pair pulls electron towards itself and the fluorine pulls electrons towards itself. Therefore net polarity due to fluorine is towards downwards, and net polarity due to lone pair is upwards. Hence net dipole moment is very much less in NF3 as compared to NH3. Therefore mu of NH3 is greater than mu of NF3. Since you know that a dipole moment is a vector quantity, therefore they will cancel each other if they are in opposite directions. Okay, so let's discuss about formal charge. Formal charge. Now, formal charge, it is the difference between the valence electron in an isolated atom and the number of electrons assigned to that atom in a Lewis structure. Okay, so the definition of formal charge is formal charge equals number of valence electrons equals number of valence electrons of an atom minus number of bonds formed by the atom, number of bonds formed by the atom minus number of unshared electrons of that atom minus number of unshared electrons of that atom. So based on this formula, you may be asked to calculate the formal charge of all the atoms in NO3. So let's draw the structure of NO3 and then let's try to calculate the formal charge of NO3. So the structure of NO3 is like this. It looks like this. Structure of NO3 looks like this. So if we draw completely the structure, then it will be like this. Now we need to calculate the formal charge on this nitrogen, formal charge on this oxygen. Let's call it oxygen A. Let's call it oxygen B, and let's call it oxygen C. So the formal charge on N equals number of valence electrons of atom. We know that the number of valence electrons for nitrogen is 5. Number of bonds found by the atom. Here the total number of bonds found by nitrogen is 4 minus 4. Minus number of unshared electrons of that atom. Since this is 0, no atom is unshared, minus 0. Therefore formal charge of nitrogen is plus 1. Hence we will assign here plus 1. Formal charge on oxygen A. Now number of valence electrons of this oxygen atom is 6, minus number of bonds formed is 2, and minus total number of unshared electrons. Total number of unshared electrons, as we can see, it is 6. It is 4. Therefore formal charge on oxygen A is 0. Now formal charge on oxygen B is 6 minus 1, since only one bond is formed, and minus 6 unshared electrons are there. Therefore it is 6. So this becomes minus 1. Hence we'll assign here minus 1. And formal charge on oxygen C is C is 6, similar to B1. 6 minus 1 minus 6 equals minus 1. So we will assign here minus 1 as well. So this is the formal charge, or these were the formal charge on these individual species. Now let's discuss one very important theory in the field of chemical bonding, and that theory is known as VSEPR theory. Now this theory says that the geometry assigned by the species is the one which minimizes the repulsion in that particular species. So geometry assigned or assumed by the species is the one which minimizes the repulsion in that species. And lone pair repulsion is greater than lone pair bond pair repulsion, which is further greater than bond pair repulsion. Therefore always give preference to eliminate lone pair repulsion first, and then eliminate lone pair bond pair repulsion, and then finally eliminate bond pair repulsion. Okay, so this theory is known as valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. So now let's see about the different types of structures that will be taken up by different types of molecules. Suppose the molecule is AB2 type. Therefore we can say that A is the central atom, and in order to minimize the repulsion, B should be linear. Because if B is somewhat bent, therefore there will be a repulsion between this B and this B, which will be greater than the repulsion between this B and this B. Okay, so therefore the greater the angle between these two species, between this B or this B, the minimum will be the repulsion, and hence the most suitable structure assumed by AB2 type structure is linear. It undergoes linear structure. And similarly, AB3, they assume trigonal planar structure. Trigonal planar structure. AB4, they assume tetrahedral structure. AB5, they assume trigonal bipyramidal. And AB6, they assume octahedral structure. AB6, they assume octahedral structure. Okay, but the story is not finished here. Suppose in case of BF3, in case of BF3 example, BF3, now B act as a central atom, and fluorine should be arranged such that the repulsion between the bonds should be minimum. Therefore, there is only one arrangement. It is like fluorine are the vertices of an equilateral triangle, and the angle between these fluorines will be 120 degree. So this is the case when only BF3 is there and there is no lone pair on central atom. But the story is not finished here. There can be the lone pairs on central atoms. And when lone pair come into existence, we always have to give preference to eliminate the lone pair or lone pair bond pair repulsion first. Okay, so the molecule, suppose the molecule has got a general formula as A, B, 2, E, where E is the number of lone pairs. So one lone pair is there, two molecules are there of one species, and A is one central atom. So suppose this is SO2. Example. If we draw central atom of such as sulfur as S here, and we give the structure to oxygen like this, like linear molecules, but there exists one lone pair of sulfur here. Okay, since one lone pair is there, therefore it will exert some amount of repulsion with this bond pair and with this bond pair. Okay, and since repulsion is there, therefore these bonds will tend to be bent. These bonds will shift and it will be like this. Therefore the correct structure for SO2 is, this is lone pair, this is positively charged electron, and here this is bent or angular shaped. So this correct structure is bent, not linear. This is wrong. This is right, because this structure minimizes the repulsion between lone pair and bond pair, which should be our priority first. Okay, so there are many other structures. For example, AB3 type, NH3. For example, there is NH3. Example, NH3 type. There is a lone pair for with nitrogen, and hence hydrogen should be arranged such that they occupy the corners of a tetrahedron, and hence this molecule is trigonal pyramidal. And the structure is AB3E type. So therefore we are not going to discuss further structures like AB4E or AB2E2. Just keep in mind that the structure should be such that the repulsion gets minimum. Okay. Now, as we know that covalent bond, whenever covalent bond is formed, they are characterized by different types of bonds known as sigma bond or pi bond. So let's discuss what is sigma bond actually and what is pi bond actually. So sigma bond, it is formed by, suppose this is an s orbital. So whenever two s orbitals overlap, a sigma bond is formed. This is sigma bond. Or one s orbital or one p orbital overlap, like in this manner, then sigma bond is formed. Or two p orbitals overlap axially, then this sigma bond is formed. This is sigma bond. Whereas pi bond, they are formed by lateral overlap of p orbitals. Okay. So let's discuss about hybridization. Hybridization, it is a process, or it is a combination of certain number of atomic orbitals of slightly different energies to form the same number of new hybrid orbitals of equal energy. So suppose there is, in case of hybridization, by definition, I once again repeat, it is the combination of certain number of atomic orbitals of slightly different energies to form same number of new orbitals of equal energy. Okay, suppose there is an atom of carbon. Suppose there is a carbon atom. Example, there is a carbon atom. Since carbon since carbon's electronic structure is 1s, 2s2, 2px1, 2py1. Therefore, its valency should be 2, but this is not the case. It shows a covalency of 4. So, there is not the covalency of 2. And to justify this, a concept of hybridization was developed, that whenever carbon undergoes a transformation into excited state, then we know that 2p orbitals, there are total of 3 orbitals. This is 2px, this is 2py, this is 2pz. Okay, so in case of carbon, 2px z orbital is empty here in this case. So one electron from 2s orbital, it goes into 2pz orbital here. Since these two are filled, this is empty. So to show this, here this is 2s orbital. So this orbital is empty here. So one electron from here, it goes into this orbital and they form total number of 4 sp3 orbitals. This time, this is 4. There are 4 sp3 orbitals. There are 3p orbitals. And there is 1 s orbital. So they intermix to form 4 sp3 orbitals. Okay. So this is the concept of hybridization. In order to achieve same energy so that they can react in a regular fashion, they intermix with each other. So when 1s orbital and 3p orbitals intermix, we call them as sp3 orbitals. Similarly, when 2p orbitals and 1s orbital intermix, we call them as sp2 orbital. Or when 1s orbital and 1p orbital intermix, we call them as sp orbital. 1s or 1p intermix, we call them as sp orbitals. This process is known as hybridization. They are intermixing of orbitals. Intermixing of orbitals to form orbitals of same energy. Okay. Okay, so now let's discuss about molecular orbital theory. So let's discuss about molecular orbital theory and bond order. Molecular orbital theory. Okay, so the valence bond theory with the concepts of hybridization and resonance is used to explain the structure and properties of several molecules, but there are limitations of them. To overcome the limitations of valence bond theory, molecular orbital theory was developed. The limitations such as valence bond theory in its original form, it is not able to explain the paramagnetic behavior of oxygen molecule. O2 molecule is paramagnetic, but VB theory could not prove that. Hence, molecular orbital theory was developed. And the features of molecular orbital theory are, suppose in case of molecular, all the electrons are taken together and considered as moving in the field of all the nuclei, and there are many. So, the main postulate of molecular orbital theory was that each electron was characterized, each electron was characterized by psi. Psi is the wave function, or we can call it as atomic orbital for that electron. Remember that psi contains all the information that is required for an electron. So suppose there are two orbitals, psi1 and psi2. They combine linearly to form a molecular orbital. They combine linearly to form molecular orbitals. They form combine linearly, they form molecular orbitals, and the combination, linear combination, is of the form psi1 plus or minus psi2. Therefore, two orbitals, they combine to form two other orbitals of different energies. So psi1 and psi2, they form, first is psi1 plus psi2 orbital. It has got an energy higher than that of psi1 and psi2 individually. And other orbital is formed as psi1 minus psi2 orbital. Its energy is lower than that of psi1, individual psi1 and psi2. So these two orbitals, psi1 and psi2, they give two other orbitals, psi1 plus psi2 and psi1 minus psi2. And yes, energy of psi1 plus psi2 is lower than that of individual psi1 and psi2 energies. Therefore, their characteristics are that they have lower energy, and therefore they are known as bonding orbitals. Bonding orbitals. And their energy is higher energy. They are known as anti-bonding orbitals. As an electron first prefers to go to a lower energy level than that of higher energy level, therefore psi1 plus psi2 is preferable than psi1 minus psi2, and therefore psi1 plus psi2 form bonding orbitals. Okay. Now, when s and s orbitals they combine, when s and s orbitals combine, they give us one bonding orbital, that is bonding orbital is sigma s, and one anti-bonding orbital that is sigma s star. Similarly, when pz and pz they combine, they give us sigma pz as bonding orbital and sigma star pz as anti-bonding orbital. Anti-bonding molecular orbital, or simply orbital. Well, there are many other types of bonding and anti-bonding. For example, when px combines with px, they give pi px as bonding and pi star px as anti-bonding. Okay, so based on these studies, molecular orbitals were arranged in the order of increasing energy, and the electrons are filled based on Bohr principle. That is, molecular orbitals are occupied in the order of increasing energy. So molecular orbitals are arranged as sigma 1s, sigma star 1s, sigma 2s, sigma 2s, sigma star 2s, sigma 2pz, pi 2px. Its energy is almost equal to pi 2py. And then there comes pi star 2px. Its energy is almost equal to pi star 2py. And the energy of sigma star 2pz is higher, and it goes on. So this is for the atoms or molecules in which the total number of protons is smaller than 14. That is for N2. So remember this table, because questions are asked based on this table in IIT JEE. Now, Hund's rule of maximum multiplicity or Pauli exclusion principle, everything is valid on molecular orbital as well. Okay, so suppose now this is bonding, this is bonding, these are bonding orbitals, this is bonding, and others are anti-bonding. This is anti-bonding, this is anti-bonding, these orbitals are anti-bonding. So in any molecule, suppose there is n molecules in bonding atomic orbitals, n electrons in bonding atomic orbitals, and n dash electrons in anti-bonding atomic orbitals. So there is a term known as bond order. Bond order. And it is defined as number of electrons in bonding molecular orbitals minus number of electrons in anti-bonding molecular orbitals divided by 2. Okay, so this is the case when bond order, to calculate the bond order, this is the formula for any molecule, and bond order shows us, or it signifies us, the total number of bonds that's there between the atoms of that particular molecule. So therefore bond order is used to calculate whether a given molecule is stable or not. Suppose we are given with helium. Suppose we are given with He2 molecule. So does it exist? Does He2 molecule exist? Let's see. In case of helium, there are total of 4 electrons. Okay, so 4 electrons, they will be arranged as, in case of helium, sigma 1s2, sigma star 1s2. That's it. 4 electrons are finished. So therefore, bond order is total number of electrons in bonding molecular orbitals, that is 2, minus total number of electrons in anti-bonding, that is 2 upon 2. So this comes out to be 0. So since bond order is 0, molecule He2 does not exist. Okay, so bond order is always a positive quantity. It is never 0 or smaller than 0. And therefore, for O2 molecule, the distribution of electrons will be like this: 1s2, 1 or to be more precise, let's write sigma 1s2 sigma star 1s2. The total number of electrons are 16 here, 8 from each oxygen. So there will be sigma 2s2 sigma star 2s2. So total molecules have been 4. Okay, after sigma star 2s there is sigma 2pz, and then pi 2px and 2py. So here will be sigma 2pz, and now there will be filled pi 2p pi 2py. 1 electron will be filled here, 2 electrons will get filled, and then pi 2p here pi 2px and then pi 2py will get filled. Here it is pi 2px, or this is pi 2px, and here pi 2py will get filled 1. And since more electrons are left, 2 plus 2 plus 2 plus 2, there are 8 to 10, only 12 have been there, so 6 more electrons are left here. So therefore plus 1 plus 1, another will get filled based on Bow principle and Hund's rule. Okay, so after that there exists pi star 2px, whose energy is almost equal to pi star 2py. Okay, so the total number of molecules now gets filled is 1 here. Now what have been the total number of molecules so far? 2 plus 2 plus 2 plus 2, 8, 10, 12, 14, 1, 15, and one more electron is going to be filled, and it will be filled here because both of them have got same energy. Now since in these orbitals 1 electrons are there in each, therefore this molecule is paramagnetic, and hence this molecular orbital theory, it explains very beautifully the paramagnetic behavior of oxygen molecule, because there is only one electron in 2 orbitals. Since electrons are not paired, therefore it is not diamagnetic, even though it is an even numbered molecule in which the number of electrons are even. So bond order in this case is total number of electrons in bonding orbitals. So bonding orbitals are 2 plus 2, 2 plus 2 plus 2, 6, 7, 8, 9, 10, that is 10, minus 2 plus 2, 4, 1 plus 1, it's 2, that is 4 plus 2 is 6, 10 minus 6 upon 2, so this comes out to be 4, and hence there are 2 bonds in between oxygen atoms. Therefore structure of oxygen is like this. We can conclude it from bond order. Okay. So let's discuss 2 questions. There are 1 or 2 questions that have been asked on bond order, since they are good. So let's discuss them. So first let's discuss the question on BSc PR theory. It was asked in IIT JEE 2010, IIT JEE 2010, that number of FBRF angles in BRF5 whose value is 90 degree. We are asked to find this number. Okay, since BRF5 is there, therefore one thing can come in your mind, the structure of BRF5 as BRF, there is 3, and then there is 1 above the plane F and below the plane F. But this is not the case, because bromine has got 1 lone pair, and since in this structure there is no space to accommodate lone pair, therefore this is not the correct structure. Therefore correct structure can be to get some space for the lone pair of bromine. This is This can be the correct structure. Above here it is fluorine, or below it is the lone pair. Okay, so from this, looking at this, you can say that there are that total number of 90-degree angles are 1, 2, 3, 4, etc., etc. You will start counting, but this is not the case here. Since lone pair is there, it is exerting a force of repulsion on these 4 bond pairs, and therefore these will get distorted. These 4 bond pairs will get distorted, and hence the correct structure in this case is bromine with its lone pair here, and the fluorine atoms as distorted ones. So they will form a rectangle type, okay, but there is no, from VSEPR theory, no 90-degree FBRF angles. So this is the correct answer in this case. Okay. So there was one question asked in IIT JEE 2007 that we were given with 4 compounds, that people were given with 4 compounds, that is Na2O2, O3, N2O and KO2. We were asked that which is paramagnetic. Which compound is paramagnetic? Okay, so in this case, in case of O2, 2 negative, let's see how the electrons are getting filled. Here, since the oxygen is in the form of O2, 2 negative, so let's see, in case of O2, 2 negative, the electrons are getting filled as sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2, its energy is almost equal to pi 2py2, and then total number of electrons has been 2 plus 2 plus 2 plus 2 plus 2, that is total 10, plus 4, 14. Now since total number of electrons here are 14, oh sorry 18, 16 from O2 and 2 extra electrons, so total number of 4 electrons are still needs to be fulfilled. And now after this energy level there comes pi star 2px2, its energy is almost equal to pi star 2py2. So therefore in this case no unpaired electron is there, therefore this is not a paramagnetic. This is not a paramagnetic compound. Okay, but to account for the further question, okay, since in case of N2O or in case of O3 or in case of KO2, in case of O3 total number of electrons are 24. In case of N2O, the species is just O2 negative, and in case of O2 negative there will be total 10 electrons and it will be filled up to here. So in case of O2 negative also there will be no unpaired electrons, hence this will also not be paramagnetic. O3, it will also not be paramagnetic if you take this further. So in case of KO2, let's see what happens in case of KO2. In case of KO2, oxygen exists as O2 negative. So if we release one electron from here, from O2 2 negative, then one electron will get shorted from here, pi star 2py orbital. So finally, after all this, the last structure would be pi star 2px2 and pi star 2py1. and everything will be same as this. Okay, so therefore we can see that in one orbital there is one unpaired electron, and hence it is paramagnetic. Therefore remember, in case of oxygen, O2 positive is paramagnetic, O2 is paramagnetic, and O2 negative is also paramagnetic. Okay, so this question was asked in IIT JEE 2007. Okay, so one more question, it was asked based on the bond order. On the basis of ground state electronic configuration, arrange the molecules in increasing bond length order. Okay, so the question was arrange the molecules in increasing O-O bond length order, and the molecules were KO2, O2, O2, AsF6. Okay, so in case of O2, the electrons were filled as sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2px2, and then here it was, after that it was pi 2py2, pi 2pz2. Their energy is almost similar, and then there was pi star 2py1, and then pi star 2pz1. Okay, this is how in O2 it gets filled. Therefore bond order is 10 minus 6 upon 2 equals 2. In similar fashion, if you go for calculating bond order of O2 negative and O2 positive, in this case it exists as O2 positive, in this case it is simply as O2, and in this case it is exists as O2 negative. So if you go on calculating the bond order for O2 negative, you are just filling one more electron in anti-bonding orbital. Therefore bond order in this case is 10 minus 7 upon 2 equals 3 by 2 equals 1.5. And in case of O2 positive, you are just taking off one more electron from anti-bonding orbital. Therefore there will be 5 as the number of electrons in anti-bonding orbitals. Therefore in case of O2 positive, bond order is 10 minus 5 upon 2 equals 5 upon 2. And hence, therefore, since bond order is O2 positive greater than O2 negative, therefore bond length order is O2 positive smaller than O2 negative. So this is the correct answer, and this question was asked in IIT JEE 2004. So mainly very theoretical questions are asked in IIT JEE. Just have your good grasp on concepts like VSEPR theory or valence bond theory, especially their limitations and why they were introduced, and the molecular orbital theory, of course, very important concept. So that's all for this video. Thanks for watching.